Okay, so in this video what I'd like to do is tell you how the speed of light experiment is run and talk a little bit more about this transmitter receiver box over here and what some of our signals and data will be. So as the apparatus is set up here, this is essentially how the experiment works. You have the transmitter receiver over here, the Fresnel lens right here for some focusing, and the retroreflecting mirror or reflector over there. So what happens is the transmitter transmits a pulse of light out. It travels this way through the Fresnel lens, out of the Fresnel lens, off the reflector, back this way into the Fresnel lens, back again, back into the box for detection. And so you can see that if you could somehow time how long it takes the pulse to leave the aperture, travel through its path, and come back again, that would be like a delta t, some travel time. Then, if you just measure the distance between the transmitter and the reflecting mirror and back, so maybe twice this outgoing distance out and back, you could have the distance. And of course, speed then is distance over time. So it is a so-called time of flight measurement. You're just measuring how long it takes a pulse of light to travel a certain distance, dividing the distance by time, as we said, and no gives speed. So that's essentially how the experiment works. And so to generate the data set, generally we leave the Fresnel lens as is here because it does a pretty good job at collimating when it's placed at one focal length away from the transmitter. But in practice what we do then is we sort of move this mirror at different positions past the Fresnel lens to generate some different path differences for the light to travel. And so that's essentially where the data is going to come from. So what we'll do now is let's talk about the signal that we get from doing just this. Okay, so if I zoom in a bit on the oscilloscope, what we see a couple pulses on there, and I'd like to tell you where those come from. So if I go back over here to the transmitter receiver box, there's a little schematic on the side of it that's definitely worth taking a look at to see how it operates here. And so what you can see on the side is there's three outputs on the back of the box here where these wires are. I'll show you those in a second, but there's basically outputs A, B, and C. So somewhere internally there's a bright flash of light that happens. And then what happens, and the bright flash is sent this way towards the aperture. And so what happens is you can see here as there's sort of a beam splitter drawn on the schematic right here that says, okay, if light is coming out along this direction right here, let's let it hit the beam splitter, and what it'll do when it hits the beam splitter, it immediately goes to output B. What does that mean? It means as the light is about to leave, part of it is peeled out of the main beam and sent to the detector on output B. And if output B is then routed to the oscilloscope, then we can immediately have sort of a timestamp or a time reference about exactly when the light pulse left the aperture. That's sort of like our t is equal to 0. The seeing its pulse on the B output is t is equal to 0 essentially. And so what I have over here on the oscilloscope is I have the B output from the transmitter receiver box going out here onto channel 1, and so indeed you can see there's the pulse of light leaving the transmitter. So there's nothing, 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 nothing. Suddenly the internal electronics tells the LED to flash just as it leaves the aperture. Some of it's peeled off on that beam splitter to output B. There it is. The beam passes, goes out, and off it goes. So here, this is sort of when the pulse is leaving the apparatus. Over here is when it's traveling through the room or down to the retroreflecting mirror in there. So then if we go back to the schematic that you see on this box here, then once again, you can see that as light comes back into the aperture here, it hits that same beam splitter, but because of the orientation of it now, it's going to reflect up into detector A. So A, B, and C is sort of, or B and C anyway, are all detectors. And so you can see that B does that detection on the way out, but A does the detection just as the pulse comes back in. So it comes back in, hits the beam splitter, goes up to output A. And so if I go back over here to the oscilloscope now, I have output A on channel 2 of the oscilloscope, and I just turned it off, but I'll turn it back on here. So there's the oscilloscope again. So if I turn channel 2 back on, this green pulse you see down here is the pulse coming back. And so I hope you sort of see how the experiment would be run then. The top one is channel 1, or the B output. That's the pulse going out. The green one or bottom one is channel 2, or the A output, which represents the pulse coming back. So of course the question then is, if light's traveling down the table here as advertised, why are these two pulses right on top of each other like that? And And of course the reason is that I have a very sort of close proximity mirror at the moment here. So if the light source is right here and the reflector is right here, it looks like, if I'm estimating, I have like less than a meter between them. And remember, that light travels at about 1 foot every nanosecond, or about, remember, the 300 million meters per second. And so 1 foot per nanosecond, let's see, this is about 2 feet that I have here. There's going to be something like one or two nanosecond delay between these two pulses here. And there probably is, but it's just kind of hard to see on the oscilloscope. So if I sort of do this a bit, I can expand the graph here. Maybe there's a slight delay between the peaks. This one seems like it's peaking right here. This one might be peaking over here. There might be a slight delay between them, not much. But the moral that I'm trying to tell you here is to really start seeing those peaks separate, we need to move this mirror farther away. Okay, so I'll do that in the next video. I'll sort of run through some generic data taking, but let me just take one more last look at this box here. I hope you're getting the gist of how all this works. And let me just go over that last output right here. So we covered B, grabs the light as it's just leaving. We covered A, grabs the light as it comes back. C here is a detector also that always tells the oscilloscope, or always sends a signal out whenever the LED flashes, whenever it flashes. That's another sort of synchronization source you can use to send back to the oscilloscope to trigger if you want. But in this case, I don't know, I prefer just to say trigger the oscilloscope right when the pulse leaves this box on channel B. And so it's no big deal, but if you sort of look in the back here, you can see once again the cabling right here. I think you can see, oops, that didn't too clear, is it? How about maybe this will work? Can get a little focus now. Okay, there's some focus right there. You can see, maybe you can't see the labels, but this is my B output right here. Here's my A output right here. And those are just routed to the oscilloscope into the respective channels. C is this one right here, which we're not using at the moment. So see, it's all pretty simple. Or I shouldn't use the word simple. I say straightforward, I guess. That the box sort of takes care of all these sort of little issues for us. Okay, so in the next video, I'll show you how the data comes in and how we can make those pulses separate a bit more.